Welcome to this Stories lecture. Today I'll talk about new and emerging battery technologies. This lecture is part of the Stories lecture series on energy storage technologies and especially hybrid energy storage. Stories is a large European project consisting of industrial partners as well as research institutions and academia. In Stories, we aim at promoting hybrid energy storage as a means to achieve better and more efficient energy storage solutions. I'm Poul Norby. I'm from DTU Energy at the Technical University of Denmark. My research is founded on an interest in functional inorganic materials, especially materials chemistry, synthesis of materials, and relationship between crystal structure and properties. In situ and operando studies, especially using synchrotron X-ray and neutron radiation, has been one of my main interests in many years. At DTU Energy, our battery research is based on close collaboration and interaction between synthesis of materials, structural and electrochemical characterization, and computational methods and modeling. We believe that this combination is a strong combination for battery research. I'll show just a few examples of some of the research topics that we're interested in within operando studies of batteries. We have studied, for instance, the homogeneity of lithium distribution in a prototype multi-layered battery cell. The cell contains NMC811, which is a new cobalt-poor layered cathode material. On the anode side, we compare conventional graphite with a silicon graphite mixture and look at the pristine and heavily cycled battery cells. So our main interest is lithiation, delithiation properties and battery degradation. On the left side here we see the results from a spatially and time-resolved synchrotron X-ray diffraction investigation. The colors represent the crystallographic A-axis in NMC811. And this correlates with the lithium content. If we look at the battery with a fixed A-axis scale, we can see that even after 200 cycles, the charge-discharge performance looks very homogeneous. The batteries, which were made by CDTech, were actually very good. However, if we use a variable scale, the homogeneity of the lithium distribution becomes much more apparent. The right-hand side shows a study where we followed the phase distribution between zinc and zinc oxide in a rechargeable zinc air battery. The battery cell was built in a capillary, giving access to perform spatially and time-resolved synchrotron X-ray diffraction studies. The map shows the phase distribution as a function of time and height in the anode, given as weight percentage of the zinc metal. As the discharge progresses, a reaction gradient is clearly developing through the anode. On the following charge cycle, reduction of zinc oxide to zinc is observed, leading to a more complex phase distribution gradient. With the implementation of more and more sustainable energy production, the intermittent nature of solar and wind energy makes it necessary to develop efficient energy storage solutions. Energy storage must cover long-term as well as short-term storage. It's clear that batteries will play an important role in the future energy storage system, but they can only cover short-time storage, hours, days, maybe weeks. In personal transportation, batteries will dominate. But for larger energy storage system, it's necessary to use a combination of energy storage technologies. This is at the core of the storage project. Energy storage in a large-scale electricity grid will consist of several technologies where batteries will contribute. Batteries will especially contribute to short and medium-term storage. This could be frequency regulation, voltage stability, They are very fast reactions in the order of seconds and minutes. Peak shaving, where the demand for electricity exceeds the production, for instance in the late afternoon, that's an example of storage requiring hours. Local storage, for instance in houses, villages, small islands, is another example of using battery energy storage. The full advantage of energy storage systems can only be realized by combining energy storage technologies. Chemical, mechanical, electric, thermal, magnetic energy storage are examples of complementary storage technologies where a powerful hybrid energy storage system can be built to cover various time and size scale requirements. As an example, we can look at combining battery storage with chemical storage, for instance, production of hydrogen or synthetic fuels, and thermal energy storage, which can then be utilized, for instance, in district heating. Let's take a look inside the battery and look at the principle of rechargeable batteries. Here's, for instance, a lithium-ion battery consisting of a positive and a negative electrode, separated by an ionic conducting electrolyte and a membrane separator. When discharging, the electrons running in the outer circuit as a current performs work. The lithium ion is then transported through the electrolyte, maintaining the charge balance. The positive electrode we often refer to as the cathode, while the negative electrode is referred to as the anode. The energy storage in the battery is stored as chemical energy, so we can think of it as a redox reaction waiting to happen. Only when the outer circuit is connected, then the reaction is allowed to proceed, releasing the stored energy as electrical energy or receiving the energy for storage. The positive electrode contains typically a transition metal, for instance, iron, cobalt, manganese, which can easily change oxidation state. The negative electrode contains typically graphite, where lithium ions can move in and out, again allowing electron transfer from the electrode to the outer circuit. The materials are often layered materials where intercalation, which is insertion of species between the layers, can easily happen. And this happens without breaking in the strong bonds in the metal oxygen bonds in the layer. It just moves the layer a little bit closer or further apart. If we look at the lithium-ion battery, it's important to realize that there are many different chemistries that can be involved. There's a multitude of reactions and electrolytes which are involved. This is different from earlier battery technologies. For instance, the lead-acid battery has undergone many improvements, but the chemical reaction taking place are the same as when it was invented in the 1850s. Also a nickel-cadmium battery. There's only one possible chemical reaction involved. So here are some of the typical electrode materials found in lithium-ion batteries. The LCO, lithium cobalt oxide, was the original cathode material in lithium-ion batteries. It's a layered material structurally similar to present-day NMC materials, and they contain a mixture of nickel, manganese, and cobalt. NMC does not only have a reduced cobalt content, but it's also far superior as a cathode material because it has higher specific energy and much better durability and cycle life than the lithium cobalt oxide. The spinel materials related to lithium manganese oxide are three-dimensional materials. The LNMO material, where some of the manganese have been substituted with nickel, is one of the promising future cobalt-free cathode materials. Another cobalt-free cathode material, which is increasingly used in batteries for electric vehicles, but also dominating in stationary storage, is lithium iron phosphate, LFP. It's also a three-dimensional structure which is very durable, but with lower specific energy compared to NMC. The electrolyte in lithium-ion batteries is typically an organic solvent with a dissolved lithium salt, for instance, lithium hexafluorophosphate. If we look at the structural representation of the three types of positive electrode materials, we can see that it's shown as coordination polyhedra for the transition metal, which is coordinated to oxygen, and then phosphate group. The transition metals are coordinated octahedrally to oxygen, and is shown as the octahedra in this structural representation. In LFP, the phosphate groups are shown as yellow tetrahedra, binding the structure together. The more mobile lithium ions are shown as spheres. The layered material is an example of classical intercalation material, where insertion and deinsertion of lithium ions between the layers in the two-dimensional structure only changes the distance between the layers. It's important that no major structural changes take place, which gives a low activation energy for the process. It does also mean that there's a limit on the lithium content. If there's not sufficient lithium between the layers, the structure becomes unstable and transformed to another crystal structure. So therefore it's not possible to utilize 100% of the intercalation capacity, but maybe only 80%. The three-dimensional spinel structure has the composition 1 lithium, 2 transition metals, ions, and 4 oxygen, as for instance LiMn2O4. Here it's possible to come close to extracting all the lithium ions, as the empty spinel structure is sufficiently stable to maintain its structural integrity. As can be seen from the chemical composition, only 1 lithium is available for each 2 transition metal atoms. This reduces gravimetric capacity. On the other hand, the voltage when you're using nickel is high, and this results in a gain in the specific energy available. Lithium iron phosphate is another three-dimensional structure where the iron phosphate forms a three-dimensional framework. Again, this means that 100% of the lithium ion present can be used. However, phosphate groups are not redox active, and they add to what we can call the dead weight, limiting the specific capacity. Also, the available voltage is limited due to utilization of the iron 2 iron 3 redox reaction, and this gives us lower specific energy. There are many new emerging battery technologies. They have to compete, though, with the very successful lithium-ion battery. Some of the advantages of lithium-ion batteries are, for instance, the price. Battery prices has gone down dramatically for the lithium-ion battery. More than 80% price drop from 2012, and the price is now below expectations from just a few years back. If we look at the curve, there was a small increase in price in 2022 due to raw materials prices increasing. Now the prices are decreasing again. This is actually one parameter which makes it very difficult to compete with the lithium-ion technology. The high round-trip energy efficiency of lithium-ion batteries is also difficult to match with other battery technologies. However, for stationary storage, this may not be too important as long as the price is low. Several of the upcoming battery technologies may actually compete on specific energy and energy density, and with time also on durability and cycle life. One great advantage is that the lithium-ion battery production is very well established over many years, and it's automatized, and that has taken a long time to establish. New battery technologies, for instance sodium-ion, which can use the established production technology, may have a big advantage here. Safety is of course a parameter where new battery technologies can make a big impact. I put safety both as an advantage and a disadvantage for the lithium-ion batteries. They have become very safe, and efficient battery management system has been developed. However, fire hazards is still an issue with lithium-ion batteries, and new technologies must be able to have an even lower fire hazard. Especially for large stationary storage energy facilities, fire hazards must be reduced significantly. One of the disadvantages of lithium-ion batteries is also a question of resources. This means availability, abundance, price toxicity, and also environmental and working conditions in obtaining the materials. This is a challenge, for instance, for cobalt. Let's look at some of the emerging and existing battery technologies which will have an impact on energy storage in the coming years. Some of the technologies suitable for large-scale storage are redox flow batteries, which are already available, and the sodium-ion batteries, which are interesting also for transportation. Then the solid-state batteries, a technology which has been promised for many years and which will potentially make a very significant impact on energy storage. I'll talk also about another group of battery technologies, namely the conversion type batteries, especially focused on lithium sulfur and metal air batteries. If we look at redox flow batteries, they are already operating in many places in the world in connection with grid-scale storage or local energy storage. At the moment, it's mainly the vanadium redox flow battery which is operating. In the redox flow battery, the energy is stored in solutions in big tanks, and the redox process is utilized in a flow cell which operates actually much like a fuel cell. The main present commercial solution is vanadium based. One tank utilizes the vanadium oxidation states 2 and 3, and the other tank utilizes the vanadium oxidation state 4 and 5. The main advantage is that it's very easy to scale between power and energy. If more energy content is needed, more tanks can be added. If more power is needed, more reaction cells can be added. The redox flow battery is very suited for large-scale stationary storage. The specific energy and energy density is low, but that's okay for stationary storage. There's no fire risk associated with the present redox flow battery, as they are using aqueous solutions. Price and resources are of course important elements. Vanadium-free flow batteries are being developed using, for instance, iron or organic molecule, which hopefully will make them cheaper and less demanding of resources. Sodium-ion batteries. They are very similar to the lithium-ion battery. It's an intercalation battery. It has an organic electrolyte. It utilizes transition metal oxide as a cathode and a carbon-based anode. For sodium ions, intercalation into graphite does not actually work. So the anode material used is mainly another type of carbon, a disordered hard carbon. The advantage of the sodium-ion battery is that we can use sodium instead of lithium. meaning that we have a much more abundant and geographically accessible resource. It's also possible that the cathode material can be made using more abundant transition metals such as iron and manganese, which is much less problematic than, for instance, cobalt and nickel. In lithium-ion batteries, we use copper as the current collector on the negative electrode. In sodium-ion batteries, we can use aluminium for both electrodes. The sodium-ion battery production will be very compatible with existing production facilities. They are so similar to lithium-ion batteries that it makes it easy to start a large-scale production. All in all, production costs should potentially become lower than for lithium-ion batteries. Some disadvantages are that the specific energy that will be lower than for lithium-ion batteries. It could probably come close to LFP, lithium iron phosphate batteries, making it possible to use them also for transportation purposes. As hard carbon is presently more expensive than graphite, this may be a disadvantage. This situation will probably change with volume production, and also there's some hope that hard carbon may be produced from bio-waste, making it less expensive. Like in lithium-ion batteries, we can use several types of intercalation materials for sodium-ion batteries. Here are some of the most important materials types. We have a layered sodium transition metal oxide. It's similar to NMC, and it offers high specific energy. For the sodium-ion batteries, as I mentioned, there's a possibility of using iron manganese materials, and that would result in materials using less critical resources. Then there are the Prussian blue related materials. They are three-dimensional structures based on the iron hexacyanide elements. The three-dimensional nature provides good stability and easily de-intercalation of sodium ions. A third option, which I call here the polyanionic materials, this could be, for instance, phosphate, like the sodium iron phosphate, similar to the lithium iron phosphate. It could be silicate, it could be sulfate. And again, the iron former has three-dimensional framework allowing intercalation of sodium into the structure. The structural rearrangement and phase transitions in electrode materials during intercalation and deintercalation are actually very important for the properties and the performance of the materials in a sodium ion and also in lithium ion batteries. One example is that the layered cathode materials for sodium ion batteries have a richer phase diagram with a lot of structural rearrangements compared to lithium ion batteries. Here's an example of an observed powder diffraction pattern during charge and discharge of a layered cathode material. So we see the diffraction pattern and how the diffraction pattern changes during charge and discharge. The charge-discharge curves are shown to the right with a vertical time axis corresponding to the diffraction pattern. So the diffraction pattern represents the crystal structure of the material, and we can observe that changes in unit cell parameters seen as the angular shift of the diffraction peak, and we can also see that we have phase transitions where some diffraction peaks changes and other diffraction peaks appears. A solid-state battery is actually a modification of the current metal-ion battery. Instead of a flammable liquid organic electrolyte, we use an ion-conducting solid. This could be an organic polymer, but also an inorganic solid material. Solid-state batteries are being developed and researched, and there are much activity on the research into solid-state battery. All solid-state battery in large amounts are available for large-scale applications as yet. The first solid-state batteries will be lithium-ion batteries, but could also be developed, for instance, sodium or potassium-ion batteries. If we look at solid-state batteries, normally it uses intercalation type cathode materials, but it could actually use metallic lithium on the anode side, which will give an advantage in the volumetric energy density. There are many advantages of solid-state batteries if they develop as we hope, but there are also many challenges in developing these solid-state batteries. One advantage for the solid-state battery is that the flammable liquid electrolyte is replaced by a non-flammable solid. This gives a lower fire hazard compared to conventional lithium-ion batteries. Solid-state battery could also have a higher volumetric energy density, especially when using metallic lithium as the anode. One important property of the solid-state battery is that it can operate at higher temperatures than conventional lithium-ion batteries. Conventional lithium-ion batteries may suffer from degradation, failure, or may catch fire if operated at too high temperature. We can also hope that the solid-state battery could be more durable. One of the degradation mechanisms for lithium-ion batteries is reactions between the organic electrolyte and the electrode materials. Finally, the solid-state battery could provide higher discharge rates, also because of the lower sensibility to higher temperature. But there are some issues which must be solved before that. There are many challenges which must be overcome when developing an all-solid-state battery. Most of the challenges are related to electronic and ionic transport. In a conventional lithium-ion battery, we have a porous electrode infiltrated by a liquid electrolyte. The liquid-solid interface is conformal, meaning that we have a large contact area. In electrodes and electrolytes composed only of solids, the transport across interfaces becomes much more challenging. Also, transport of ions inside a solid is much more difficult than in a liquid, requiring development of solid electrolytes with high ionic conductivity. The ions have to travel between the electrode and the electrolyte, and the boundary resistance and the contact area has to be optimized. In the electrode, we need a percolating ionic and electronic conduction pathways. This means that ions and electrons should easily be transported to the solid electrolyte and the current collector, respectively. The cathode is therefore a composite between an active material, a solid electrolyte, and a conducting phase, for instance carbon black. Contact and transportation issues also means that a solid-state battery cell may require an external pressure in order to operate optimally. The external pressure helps to decrease the interface resistance. As in a conventional lithium-ion battery, the electrochemical and the chemical stability of the components is crucial. Solid-state batteries are much more susceptible to mechanical strain, for instance from chemical expansion, from lithiation and delithiation. Again, the interface resistivity and the transport properties are critical. It was originally believed that by having a solid electrolyte, the problem with growing lithium dendrites from the anode to the cathode would be eliminated. It turns out that dendrite growth may also occur in a solid-state battery, and that is a parameter when developing solid-state batteries based on metallic lithium. One of the big challenges is the cost of solid-state batteries and the scalability of solid-state battery production. This will mean that even when the solid-state battery is being integrated in, for instance, transportation, it may be a long time before they are economically competitive. For some applications, of course, reduced fire hazard may compensate for a higher price. If we look at lithium-sulfur batteries, that's a promising technology. The specific energy could be actually a factor of 2 higher than for the lithium-ion battery. We have replaced the heavy transition metals with sulfur, and that means that the weight of the active materials can be decreased significantly. Also, if we use metallic lithium on the negative electrode side, then we can further reduce the weight. Lithium-sulfur batteries are very different from the normal lithium-ion batteries. They don't use intercalation or insertion in the electrode materials. We call this class of batteries for conversion batteries, and it also includes the metal-air batteries, which I'll talk about a little bit later. Instead of moving lithium ions in and out of the host material in conversion batteries, we form entirely new phases. An example is shown here where we have reaction of sulfur with lithium and forming lithium sulfide. So it's a conversion of the phases. It's a redox process which transforms the materials. I've shown the reaction for the lithium-sulfur battery. The true reaction mechanism is much more complex, involving, for instance, polysulfide species, which can shuttle between the positive and negative electrodes and cause self-discharge, which is one of the issues for developing lithium-sulfur batteries. It has been a promising battery technology for many years, but it has not materialized yet on a larger scale. But here's a recent press release from October this year, where Lyten has plans to build a lithium-sulfur battery gigafactory in Nevada. One of the advantages of the lithium-sulfur batteries could be that the dependence on China and Asia can be smaller regarding both the process and the materials in the battery. Metal air batteries, they are also conversion batteries. So they are called metal air batteries, but it's of course the oxygen in the air which reacts with metals. They have a very generally a very high specific energy. In the lithium-sulfur battery, we replace the transition metal with the sulfur, and here we replace the transition metal with oxygen from the air. So the metal air batteries are actually open batteries, and that means they interact with the oxygen in the air. They consume oxygen when they are discharging, and they expel oxygen when they are charging. So one special property is that if you drive with a metal air battery in your car, then the weight of the battery will actually increase as you drive, as the battery is discharged. Metal air batteries are normally very good as non-rechargeable batteries, but the difficult part is to make it rechargeable. Rechargeable metal air batteries could potentially be very interesting for transportation, but also for larger scale energy storage. They have a high specific energy, could have a high specific energy, and low production cost using abundant elements. If we look at zinc air batteries as an example, this is one of the most utilized metal air batteries. It has been dominating in the hearing aids for many years as a primary battery that's a non-rechargeable battery. So you put the battery in, it runs for a week, and then you replace the battery. In the zinc air battery, we have the overall reaction that zinc metal reacts with oxygen, is oxidized, and it forms zinc oxide. It has a very good specific energy, especially at low currents, and that is the reason why it's a very good battery for the hearing aids, because you can use it for a long time, and the currents are typically very low. To make the battery rechargeable can be a challenge. There are examples of mechanically rechargeable batteries where we reduce the zinc oxide to zinc metal externally and then load it into the battery cell. So it's basically a primary battery where we can replace the zinc metal. It's also possible to make in-cell electrochemical rechargeable batteries. There are many challenges with that, especially over the morphology and phase distribution in the battery, and also the rate that you can discharge the battery with. There are also coming some combination cells where you form metallic zinc in the battery and you store it in the battery cell, and then you transport it to the discharge cell when it's needed. This is a solution which are being commercially developed, for instance, with Abound or eZinc. Other metal air batteries could be lithium air, zinc air, aluminum air, sodium air, potassium air, iron air, a lot of interesting battery technologies. The lithium air battery is one of the battery technologies which promise the highest specific energy obtainable. It is, however, very difficult to realize, to make it energy efficient, to make it durable, to draw and charge with high currents. Another technology which is interesting for large-scale storage is the iron air battery. It has a low specific energy, but it could be a cheap and it could be a sustainable solution for large-scale energy storage. And for instance, Form Energy is looking into producing iron air batteries. Here we can see a spider diagram showing the advantages and disadvantages of different metal air battery technologies. I should maybe say that the lithium air battery, though it's a very, very promising technology, is very difficult to realize, and we need really a new way of producing and thinking lithium air batteries if we have to solve the the issues. Maybe recent reports on efficient solid-state lithium-air batteries, which could be an interesting route to take. So, as a summary, I could say that the batteries will play a significant role in the energy storage in the society, and of course also in transportation. There will be no winner of the battery race. We need to use multiple battery technologies because the different batteries are good for different applications. If we, for instance, develop batteries for large-scale energy storage, they are different than when we develop them for transportation and electric vehicles, for instance. It's also important that batteries will not be able to handle all storage needs. We need to use a combination of energy storage technologies, for instance, hybrid storage solutions, where we use different energy storage technologies closely integrated in a system. This can include, for instance, chemical energy storage, could be hydrogen, electric, could be batteries, mechanical, could be flywheels, thermal, hot storage of thermal energy, and also magnetic storage. Thank you for today.